Well, it's John Black, super chemist. We're gonna talk about what a local inertial frame is, and I didn't even know what a local inertial frame was, and I actually did a video on it without even knowing what it is, called the two types of inertial frames, uh, curved space-time versus flat space-time. I just always called it an inertial frame in a curved space-time, but it's technically it's called a local inertial frame. Okay, and I always tease Mr. Moose on my videos. He's my arch nemesis because he always disagrees with everything I say. But he actually opened up with me. We talked for a little bit, and because of that, I learned this. So I want to thank you, Mr. Moose. So let's get into it. An inertial frame. Let's first of all, an inertial frame is defined as a frame that has the simplest physics laws and the simplest math. All inertial frames have the same physics laws. Okay, so that means they all have the simplest physics laws. If one has the simplest physics laws, they all have them, right? And what gives you not simple physics laws? Well, put it this way: if you hold a ball out and you let go of it and it floats, that's the simplest math and the simplest physics laws, right? But if it accelerates down to the ground, no. That sounds like a lot of math. Okay. So, anyways, these are the 9 reasons, or whatever they are, 7 or whatever, are things that come about because you have to have the simplest physics laws and the simplest math. Everything floats. Nothing accelerates to the ground. Nothing is stuck to the ground. You know why? Because there is no ground. Ground means math. Ground means complicated physics laws. No up or down, because there's no ground. So what would be up and what would be down? And you know why there's no ground and there's no up and down? Because there's no gravity. Because gravity makes complicated math, complicated physics. Okay, constant velocity and straight line path. Okay, what does that mean? That means when you drop a ball, okay, if you have a ball and you drop it, it keeps inertial when you're in an inertial frame, meaning it just stands relative, still relative to you. Or maybe if you give it a little nudge or whatever, you're not perfect at dropping it. It might go at a constant velocity in a straight line. But it will never go in a parabola. It will never go straight down at an accelerated rate. Okay? It will always be a straight line, constant velocity. Always just remember, an inertial frame is where the ball is inertial, meaning the floating ball test, where you let the ball go in an inertial frame. It's inertial. It just stands there. So, what the hell is the difference between an inertial frame and a local inertial frame? Okay, they both have the same physics laws. So what's the big deal? How do you differentiate them? Okay, well, the inertial, just a regular inertial frame of reference is in flat space-time, where there's no planets. You're not in a gravitational field. You're just floating out in the vastness of space, okay? And as you float through space, right? You can float for everything, forever. Your balls will always be moving this way, and you will be moving that way. And we'll all be moving in parallel lines, paths. Your paths will never cross, you know what I mean? And that's what a regular inertial frame is. A local inertial frame, okay, it's not out in the vastness of space. No, it's in a gravitational field, right? So remember, a gravitational field doesn't affect objects. It only accelerates space-time down, okay? It only makes the geodesic, and the falling person just follows the geodesic at a constant speed. See down here, like down here, there's a falling ball, right? The ball is just, it's still inertial, even though his path is accelerating down, he's inertial because he has a constant speed, straight path. You might say, well, that's a curved path, but it's in curved space. So, curved, it's actually a straight line in curved space. So, Still, I'm not telling you why I'm calling it local inertial, okay? Here's the planet Earth, right? Let's say you're falling down, right? Because we gotta look at the equivalence principle, you know, that all inertial frames, you get the same whatever. Well, if this guy's falling and his balls are going to go radially, right? Things go radially down, right? Everything doesn't just go straight down. They go radially straight down. You know what I mean? So imagine you have a box here that you're floating. Okay, let's say you're in this box and this red box and you're falling down to the planet. If it's big enough, you'll see this acceleration. Okay. Now these aren't being accelerated, these balls, just like this guy isn't being accelerated. The space-time is being curved, and they're just following straight line paths, constant velocity on those geodesics, right? It's just the geodesics are radially in, right? This is what you get tidal forces from. The thing is, if your box is giant, like I said, you could figure it out, right? But if your box is local, right? It's tiny. It's a room. It's a size. That's what I always say. Got to be locked in a room. That's what they mean by local. You are locked in a small, tiny room like a house. You know what I mean? Now you're like here, and you're falling. The tidal forces, you can't tell, you know what I mean, in this little tiny box, right? Yeah, everything is, the lines are pretty much going straight down, you know what I mean? The ship is thinner than this line, basically, you know what I mean? So, yeah, you won't have this radial thing here, because you're local. Because you can only do physics experiments in a local region. Right? This guy, he can do experiments over, you know, he's not local, man. So, he'll see this acceleration. Not acceleration of the balls, of the paths, right? Because space-time is curved. So what is a local inertial frame? It's an inertial frame that's falling in a gravitational field. So to be considered inertial, like you are in outer space, you will have to be local or in a small room so that you can't see these tidal effects and these radial curved space-time thing. You won't see this acceleration. You know what I mean? And so you'll have you know. But even if you had this big room, you're still inertial, man. You're still inertial, man. Yeah, because everything is still going in a straight line in a constant velocity. So I mean, it doesn't matter if your thing is as giant as or whatever. You're still inertial, man. Okay, but when they're saying local inertial, they're saying you're in a box that's small enough where you can't realize this acceleration by paths due to radial downward gravity, you know what I mean? Now look at that. Look how I changed it. See, at local inertial is this little box. So the balls fall in straight lines, you know. He won't be able to tell that the paths are accelerating down here. Like this big box, you can tell, you know what I mean? So far we've gotten 4 types of inertial frames, okay, and one isn't an inertial frame. These 3 are all inertial frames. We have a flat space-time inertial frame, right? We have a curved space-time local inertial frame. We got a tidal force inertial frame. Okay, that's what I'm going to call that from now on. I don't know what it's called. We're going to call it that though. It's in curved space-time, just like up here. The only difference is it's big enough. Where it's big enough, it's not local. You know what I mean? You can tell that these. Look at the lines; they're different than these. But all 3 of these still have the simplest physics laws and the simplest math. These balls are going in a straight line. These are going in a straight line. Straight line. Constant speed. Constant speed. Constant speed. Everything's floating, nothing's accelerating. You can say, well, all the paths are accelerating here. The balls are not accelerating, though. This is a relative acceleration. It's not real. I mean, it's real, but it's not proper where it moves these balls into an accelerated frame of reference. Only a proper acceleration can change an inertial frame into a accelerated frame, okay? You can't just have relative acceleration and that just changes crap. Just because your paths are accelerating together, that don't mean nothing. That's just a happenstance. So why are they all inertial? Because they all have the same exact physics laws and the simplest math. You know what I mean? They all float. You know what I mean? They don't have anything to do with gravity. This one has the tidal forces, but those forces aren't forces on the ball or the man. It's the forces on the space-time to curve and accelerate down. The balls stay inertial. The man, you know, just like over here, the ball remains inertial. It's just following the paths, constant speed, you know, constant speed, and you know, standing still or constant speed with a straight path. That means that you're inertial, man. Okay, so everyone's inertial. That means you're in an inertial frame, right? If everyone's inertial, I mean, if you're accelerating in your frame, guess what? If everything accelerates, then you're in an accelerated frame. If everything stays inertial, then you're in an inertial frame. What? This isn't hard. And the last one was a relative inertial frame. That's when you have like a man on Earth. They're both in an accelerated frame, but they're in the same accelerated frame. You know what I mean? A frame that's accelerating at 9.8 meters per second squared. So relative to each other, they're standing still. So that's a type of relative inertial frame. Another type of a relative inertial frame would be like a man on a spaceship going 9.8 meters per second squared, and the spaceship itself. They're both inertial, relative inertial frames because they got the same physics and they're standing still relative to each other, just like the man on Earth. Okay, there's another type of relative inertial frame. Okay, relative inertial frame means you need two frames. This, you don't need two frames to be inertial. All you need to do is be floating. You know what I mean? You don't have to compare it to any frame. You can just compare it to the ball that you let go. Is it floating or accelerating? A relative inertial frame, right? It is two accelerating frames. But you could be on the man on the spaceship going 9.8 meters per second squared, and a man on Earth going 9.8 meters per second squared, and you can call those two relative inertial to each other if you're just doing the experiments. Like the man on the spaceships are going to, whatever experiments he does, he's going to get the same results as on Earth. You know what I mean? They're not standing still relative to each other, but their physics, since they're still in the same accelerated frame, right? They're both accelerating at 9.8 meters per second. They will both be, you know, time dilated the same. All the experiments will be the same. To be inertial, you have to be floating. So when they say in curved space-time, they don't mean in curved space-time on planet Earth, right? Because that, you drop a ball there and everything accelerates, right? They are talking about curved space-time being in a gravitational field as a free-falling object, okay? That's a local, this here is a local inertial frame, not down here on Earth, okay? Down on Earth, it's an accelerated frame because you don't have the simplest physics laws, you don't have the simplest math, and also you don't have the same physics laws as you do here or here. Everything gets complicated. Nothing floats. Everything accelerates. Everything is stuck to the ground. It sounds like a lot of math. There's a ground. There's an up and down. There's gravity. Things, you let go of it. It doesn't just go constant velocity or stand still and go in a straight line path. No. It accelerates down. It goes in sometimes straight down and sometimes in a high parabola. That doesn't sound inertial to me at all. Okay. But anyways, I want to do a shout out again to Mr. Moose. Thank you. You know, if you think I'm being mean or whatever, I'm just trying to be funny, dude. Seriously, man. Most of the stuff I do is just, I'm just trying to be funny. Yeah.